Hi folks, we're going to take a look at number 9a from page 532. So we're given this system of equations and they want us to solve it, and then they want us to interpret the result geometrically. Okay, so in other words, you've got three planes in R3. What's the nature of the intersection, or in what way do they not intersect? Okay, so I'm going to solve this using matrices instead of elimination. Okay, so first thing I'm going to do is I'm going to rewrite this in matrix form. So again, recall that I'm going to have three rows, each with four elements representing the four coefficients. Okay, and I'm going to separate out the constant terms with a line to represent that they're on the other side of the equation. Okay, so our coefficients are 1, -2, 1. Okay, and then with 3 on the other side of the equation. Okay, so here we have 2, 3, -1, and -9, and 5, -3, 2, and 0. Okay, so here's our matrix, which is just representing this system of equations. Okay, now notice here how if I were solving by elimination, I might, add rows 1 and 2, or sorry, equations 1 and 2 to eliminate the z, or here add rows 2 and, equations 2 and 3 to eliminate the y's. But here I'm going to follow the algorithm of trying to obtain that corner of zeros, okay, row echelon form, in order to establish my solution. Okay, so my system here is to always eliminate the x's first. So very happy that I've got a 1 in the top right, top left corner. Okay, it makes life easier. If I didn't have it, but I had a 1 in one of the other two rows, definitely my first step would be to interchange rows to get that 1 in the top left corner. Okay, so now let's go ahead and start with eliminating those row terms. Okay, so again, I strongly suggest that you're always adding rows together. Okay, so multiply a row by whatever it takes so that you can add rows to eliminate what you have to eliminate. So here I'm going to multiply row 1 by -2. Okay, because that's going to allow me to then eliminate that 2 in the second row. Okay, so I'm going to add to that row 2, and this new row that I'm going to form with this operation is going to replace row 2. Okay, and similarly, I'm going to multiply row 1 by -5 to eliminate that 5 there. So -5 R1 plus R2 is going to replace, R3 is going to replace R3. Okay, now keep in mind the only reason why I'm allowed to do these two operations in one step is because I'm not actually changing row 1, and that's what I'm using to change each of these other two rows. So I can't change R2 and then use R2 at the same time to change R3. Okay, so let's go ahead and do this here. So row 1 is not going to change at all. 1, -2, 1, 3. Okay, and now we've got -2 plus 2 is 0. Okay, 4 plus 3 is 7. Okay, -2 minus 1 is -3. So again, that's sort of another nice reason why adding is always nice, because then when you add that next row, you just have to look at that sign to know whether you're adding or subtracting. Okay, and here we have -6 minus 9, -15. Okay, so this is sort of our new row, or our new equation, which is replacing the old row 2, which we can do because when you're performing these operations, the new equation will still have the same solutions. Okay, so let's go to the next one. -5 plus 5 is 0. Okay, +10 minus 3 is 7. Okay, here you have -5 plus 2 is -3. Okay, so this now is already starting to look interesting, a little different from the one we did in class. Okay, so here you have -15 plus 0 is -15. Okay, and here you see that you've got two rows. It produced two rows, or two equations that are identical. Okay, so when I try to eliminate this number here, I'm going to actually also eliminate the coefficient of z. Okay, and well, we'll see where this leads, but I think we know that that might imply that there's, in this case here, infinitely many solutions. Okay, so what I'm going to do is one convention that we always have is if you have a row of zeros, or a row where the coefficients of the variables are 0 and you've got something else on the other side, we always want that on the bottom row. Okay, so what I'm going to do is I'm going to do negative R2 plus R3. Okay, and that's going to replace R3. Okay, so here we end up with 1 minus 2, 1, and 3. Okay, then 0, 7, negative 3, negative 15, and this is just going to give us 0 plus 0 is 0, negative 7 plus 7 is 0, 3 minus 3 is 0, and 15 minus 15 is 0. Okay, so what this represents is 0 equals 0, okay, which implies that there's infinitely many solutions. Okay, question is what scenario is it, which we'll talk about in a second, but now we still have to give the solution. Okay, now that we know that there's going to be these infinitely many solutions, how do we actually state it? Okay, so at this point here, I could keep going and go to what's called reduced row echelon form. Okay, so to try to get a 1 and a 1 here, and then zeros everywhere else. So my first step would be to divide this row by 7, so I get a 1 here. And we see that this is going to start creating some ugly fractions. And as I stated in class, for 3 equations and 3 unknowns, you're probably good to just stop at regular old row echelon form, which creates the triangle of zeros in the bottom left corner. Okay, so I'm going to stop here, and I'm going to now turn these back into the equations. So I'm going to start with the second row. I got 7y minus 3z equals negative 15. Okay, so here I could choose to solve for y or z. I'll solve for y just so that this thing will end up being positive there. So here we've got y is equal to 3z minus 15 over 7, so y is 3 over 7z minus 15 over 7. Okay, so here it looks like the solution is going to be a line, so I'm going to write y in terms of z, and now let's replace that into equation 1 to determine x in terms of z. So here we've got x minus 2y, so y is equal to 3 over 7z minus 15 over 7. Okay, plus z, okay, equals 3. So here we've got x is equal to, so let's bring everything to the other side. So here we have negative 6 over 7z, bring that to the other side, becomes positive 6 over 7z, and this plus z becomes minus z. Okay, and then here we've got positive 30 over 7, so bring that to the other side of the equation. Okay, is plus 30 over 7, and then of course we have the plus 3. Okay, so let's simplify this here. So 6 over 7 minus 7 over 7, so negative 1 over 7z. Okay, and then here we have 30 over 7. Sorry, I just realized there's a little mistake here. This was positive 30 over 7, so bring it to the other side, becomes minus. Okay, sorry about that. So here we got negative 30 over 7 plus 21 over 7. Okay, so that's going to give us 9 over 7, and there you have it. So again, I've written both y and x in terms of z, so I'm just going to let z be my parameter. Okay, so that means that x is equal to negative 1 over 7 t minus 9 over 7. Y is going to be 3 over 7 t minus 15 over 7. And here z is going to be equal to t. And of course, this gives me infinitely many solutions. Okay, because t can be any real value. So infinitely many solutions, but what's the geometric interpretation? Okay, well, if we go back to our original set of equations and we look at the normal vectors, by just looking at these coefficients, we see that none of these planes are parallel. Okay, so it means that geometrically what we have is that star pattern. We've got 3 planes, none of which are parallel, that intersect and align. So when I draw this dot, it's actually a line that's coming out of the page. Okay, so geometrically, what we have is three planes, or three non-parallel planes intersect and align. Okay, and always nice to include a drawing to be very clear about the scenario that we have.